When it comes to the shape of the Earth, there is the standard model where the Earth is spherical and the Sun very far away from the Earth. There is also the disc-shaped flat Earth, and in this case the Sun is very close to the Earth. But these are not the most important differences. When looking at the round Earth model, the Sun is so far away from the Earth that we can assume that the rays of the Sun are all in parallel as they reach the Earth. This means that the angle between various sun rays are essentially zero. This is not really true, because the Sun has a finite distance away from the Earth, and it also has a finite size. However, if you form a triangle between two sun rays, then the angle between the two is so minute and the triangle is so stretched out that we can assume that the angle is essentially negligible and zero. However, even though the rays are in parallel, it doesn't mean that the sun rays hit the Earth surface at the same angle. For example, in this picture, if you are in this position, then it looks like the Sun is close to the horizon. But if you move closer here to the equator, then the Sun appears to be almost directly overhead for the same moment in time. So it depends on the location of the observer as well as the time when the Sun's elevation angle is considered. For the flat Earth model, the Moon and the Sun orbit each other very close to the disc-shaped Earth. This also means that we cannot assume that sun rays are in parallel. Now the sun rays radiate out from the Sun, which is very close to the Earth, maybe 3,000, 4,000 miles. And again, depending on the location of the observer, the angle of the Sun will be different. So somebody standing directly underneath the Sun will have the Sun at 90 degrees above the horizon. However, if somebody is far away from the Sun, that angle will change and become lower with respect to the horizon. But if the Earth is flat, then the position of the Sun can be triangulated from sun elevation angles. Also, the positions of cities can be triangulated from sun elevation angles. This is true even if the Sun's distance from the flat Earth varies as it moves. In other words, the altitude of the Sun above sea level need not to remain constant for this method to work. This is basic geometry. And so a flat Earth map can easily be generated by simply looking at sun elevation angles. The question then is, why hasn't there a map been generated? Since the Flat Earth Society was created in 1956, the Flat Earth movement and Flat Earth idea has existed for centuries. Why is there still no map that we can use to plot flight paths for airliners or routes to use as our maps in vehicles? It simply doesn't exist. So here's a method with which an accurate flat Earth map can be generated by simply looking at sun angles. The tools you'll need to do this typically would be the following: a level, to make sure that any plane that you measure with respect to is level with respect to the plane of the Earth. Also to make things perpendicular to the plane of the Earth. A compass drawing tool to plot circles. A protractor to draw lines at exact angles. A degree square with which you can measure the elevation angles of the Sun directly. A magnetic compass. With this you can measure the azimuth of the Sun with respect to true north. Of course, after you've made a correction for the magnetic declination angle. And lastly, you can also rely on astronomy software or websites that produce elevation angles for the sun for any given time and even any given location. They do exist. However, this should only be used after they have been experimentally verified, and if you have built confidence in a software or website, knowing that they are not giving you false data. So it's essential that before you implement any third-party data that you have verified, that data can be trusted. In this video, we are going to eliminate many of these tools. So we're not going to use astronomy software or websites. We're not going to use a magnetic compass. We're not going to use a degree square or a protractor. Instead, we're going to use a level, a compass drawing tool, and a towel. No, that's not right. Not a towel. Try again. A NASA satellite imagery? No, not NASA satellite imagery. What we're going to use is a stick. That's right. We're going to use a level, a compass drawing tool, and a stick. No rocket science here. Just simple, basic geometry and triangulation. So let's go over some of the principles that we'll need. This equation that the tangent of theta is equal to y over x tells us how the y over x in a triangle relate to one another if we stretch the triangle in one direction. Theta is an angle. This could be either in radians or degrees. And this equation is defined by the figure. So it's an identity, and we have to use this figure, rely on the figure, and refer to that to make the equation work. You need a triangle where one angle is at 90 degrees. And this is made up by the sides x and y perpendicular to one another. Theta then is the corner of the triangle that sits opposite the side y. And you can stretch this triangle in any direction as long as you keep all the lines straight and as long as the 90-degree angle remains. This equation will work perfectly. We can also take the arctangent on either side of the equal sign and obtain a new equation that isolates theta for us. So then theta is simply equal to the arctangent of y over x. We'll use this principle when we use the stick in order to measure the angle of the sun in elevation above the horizon. In this case, we'll call the stick length y, and we'll call the shadow of the stick x. And when we take the ratio of those two lengths and the arctangent of the ratio, that'll give us theta. So what you'll do is you'll use a very level drawing surface, a vertical stick which is nice and perpendicular with the plane of the earth, and you can use a plumb line or level to make sure the stick is perpendicular. And then you'll measure the length of the stick, measure the length of the shadow, take the ratio, and then the arctangent, and that should give you the elevation angle of the sun. Now, of course, the shadow must be from the sun, casting a shadow of the stick. Just a word of caution. You may have to convert between degrees and radians. So when using a calculator or a spreadsheet to perform the math, try this. Type into your calculator or spreadsheet the sign of 90. The answer should be 1 if it is 90 degrees. But if your calculator or spreadsheet expected radians instead of degrees, you will get an answer of 0.89399. In that case, you'll have to multiply the 90 by pi over 180 in order to convert it to radians first. And then you will get an answer of 1. Conversely, if you do math and you need to convert back to degrees, you'll multiply radians by 180 over pi. In this method, we're going to have to try to locate the position on our map where our sun is directly overhead. Not the real sun, but the scaled version of the sun and the world on our map, because our map is a scaled representation of the real world, isn't it? So we're going to try to locate the position on our map where our scaled sun is directly overhead. To do that, we're going to use this relationship by assigning a value of 1 to the side y. And when y is equal to 1, then we can use this equation to find x as 1 divided by the tangent of theta long. So x is 1 divided by the tangent of theta if we assign a value of 1 to y. Now, in the real world, the sun is somewhere overhead, and we are at a certain location, and we're measuring theta. We don't know how high the sun is exactly, and so we don't exactly know how to scale it down to our map. So what we'll do is we will scale it by a convenient unit that we will pick. So suppose that you say on your map, and you have a big sheet of paper, that you're going to say that the sun is 1 meter above that paper, above the map. Then you'll call that your map unit. And then for that measurement and for that time, the distance between your location where you measure the sun angle and where the sun is directly overhead, that distance will be 1 divided by the tangent of theta meters. If you want to use a smaller piece of paper, and you say that the sun is only 10 centimeters high on your scaled version of the world on your map, then x will be equal to 1 divided by the tangent of theta times 10 centimeters. So this will be in centimeters, or you could say x is equal to 10 divided by the tangent of theta centimeters. So here's how we'll do that. We'll have the stick and the shadow with which we've determined theta. We'll extend the shadow past the stick along the line in the same direction that the shadow falls, but we'll extend it in the opposite direction past the stick by that distance, 1 divided by the tangent of theta map units. And that position, we'll mark that and use that for the location of the sun. And from that location, we can then draw circles which represent sun angles for that time, sun position, and various locations. Here's how that works. Suppose at a certain time the sun is somewhere above the earth, and we draw a line perpendicular from the sun directly down to the earth where the sun is directly overhead, and now we have a position marked where the sun is directly overhead at a specific time. Now say we are somewhere over here, and we measure an angle theta. Now we have a triangle, and if we look at the sun rays that fall in and hit the earth at an angle theta for this specific position of the sun, then all those sun rays with an angle theta lie in the shape of a cone. And where they hit the earth lie in a perfect circle. So anywhere where I can complete a triangle by drawing lines between the sun, the location where the sun is directly overhead, and the edge of the circle, will have an angle theta and an angle at 90 degrees So this is our triangle for determining the position of the sun on our map. Now what we'll do is we'll invent a map unit. And we'll call that distance between the sun and the flat Earth one map unit. Whatever that is, whether it's 10 centimeters or 1 foot or a meter, it doesn't matter. We'll call it one map unit. We can make the conversion later. And then the radius of the circle is 1 divided by the tangent of theta. So the circle 1 divided by tangent of theta radius, that red circle now represents a circle around the sun's position where sun rays hit the Earth at an elevation angle theta. How did we obtain theta? We planted a stick in our location, we measured the shadow, we obtained a triangle, and we used the arctangent of the stick length divided by the shadow length. And that's how we obtained theta. So now from theta we found the circle's diameter and radius. Now suppose that you wish to also plot the location of another city. Remember, we're going to triangulate different positions to plot a map. So we don't want to just plot one city, we may want to plot several cities or locations. Well, when you measure the sun's angle at that new city at the precise same time that you measured from your own location, and this may be by calling a friend and asking him to measure the sun at the same time as you do, then the sun hasn't moved, so we draw the same circle, but with a different radius. The same center position, a different radius. And the new radius is simply 1 divided by the tangent of the elevation angle measured from the other location. Now from where you're standing, you can now, if you ask your friend for the angle, you can plot the circle of where he is, but you don't know exactly where on this circle you must place him on your map. So all you know at this point is that your friend who did the measurement for you in another place lives somewhere on this circle. In order to pinpoint his position, we'll have to do measurements at another time. Now this is completely optional, but I recommend doing this because you get 2 cities on your map for the price of 1 measurement. Other than that, you don't really have to use it, but we'll see later it has another advantage as well. And this involves finding a position or a location or a city on the Earth where the sun would be directly overhead a specific time that you can also measure the sun from your own location. For example, the city of Santiago in Baja Sur, California, in Mexico, lies almost directly on the Tropic of Cancer. This means that on the June summer solstice, sometime during that day, the sun would be almost directly overhead the town of Santiago. So if you were taking measurements at that moment, when the sun is directly overhead Santiago, then the position of Santiago can be plotted on the map where the sun would be directly overhead, as we saw in the previous slides. And if the Earth is flat, then Santiago can be used to adjust any variation in the sun's distance to the Earth. We'll see how that works later. Now you don't have to use Santiago. You can use any town between the Tropic of Cancer and the Tropic of Capricorn, and any time when the sun would be directly overhead that location, as long as you can also see it from the other locations that you're measuring sun angles from at that time. Otherwise, if the sun is not visible from the other places, it will not work. So basically this is what we're doing. We're just repeating what the experiment, but when we find the location of where the sun is directly overhead at a specific time, that would be the location of, in our example, Santiago Baja Sur in Mexico. So here's how that works. Let's suppose the sun is directly over Santiago on June 21st at a specific time. And our location is the center of those three cities. Now the sun hits our city at a certain angle, and the sun rays that hit the earth at that particular angle will all hit the earth in the shape of a circle. Now on our map, we'll be using a stick. So we plant a stick in our location, we measure the length of the shadow, and we obtain theta by taking the ratio of the stick length and the shadow length and taking the arctangent of that. Gives us theta, the elevation angle of the sun. Then what we do is we extend the shadow in the opposite direction past the stick by a distance 1 divided by the tangent of theta map units. We can mark that position, and that is the location where the sun is directly overhead. And where do we know the sun is directly overhead at that moment? Because we picked that moment like that, is Santiago. The red circle represents the sun rays that hit the earth at the elevation angle that we measured from our location. Now, suppose that we are also able to measure sun angles at the same moment from another city. We get a new elevation angle that was measured from that city, and we can plot a new circle around the sun. Because all the sun rays that hit the earth from the sun at that angle lie in the shape of a circle. And we can do it for a third city. I will call these cities blue and black, with our own city given in red circles. So we have our location, we have Santiago's location already, but we need to find the locations of the other two cities. At the moment, we don't know where the other locations are, except that one city lies somewhere on the blue circle, and one city lies somewhere on the black circle. So what we do is we take a measurement at a new time. The sun has moved somewhere, and now we take new measurements and we repeat the process. The angle of the shadow has changed, the length of the shadow has changed, because the sun is in a new position. So what we do, just like before, we extend the shadow of the stick in the opposite direction past the stick by a certain distance equal to 1 divided by the tangent of theta map units. That marks the center of all the circles that we're going to draw, because that is where the sun is directly overhead on our scaled version of the Earth, which is our map. So we can plot a circle, again in red for our location, with that radius, and that passes through our location. Now suppose that we also ask somebody in Santiago to obtain a measurement for the sun angle at the same instant in time. In other words, he can also use a stick, measure the stick's length, measure the shadow's length, get the ratio, get the arctangent of that ratio, and give you that answer. Or he can just give you the stick's length and the shadow length, and then you can calculate it. And so you draw a new circle for Santiago's elevation angle. And immediately in this figure, in this example, you notice there's a problem. We know Santiago lies over here. We also know we measured a sun elevation angle from Santiago. But when we plot that sun elevation angle, it's not passing through Santiago, even though we know they all must lie in a circle, and that's the only place that they can be. So this circle is somehow not measuring up to where Santiago is. Something is wrong with our measurement. Something is wrong. So a possible explanation is, what if the sun's altitude changed from one measurement to the next? You see, we still assumed the sun is 1 map unit away when we plotted the red circle and its radius, and when we extended the shadow. So we may have to adjust that to accommodate any changes in altitude of the sun. Let's look at what happens when the sun is moving at different heights. In this figure, the sun is 1 map unit away from the surface of the map. And the radius of the circle of sun rays is 1 divided by the tangent of theta map units. Now, without changing anything, without changing the length of the shadow or the direction of it, suppose that the sun was actually lower. So from the viewer's perspective, who is sitting there with a stick, he cannot see that the sun is in any different position. For to him, the sun is in exactly the same position. For that to happen while the sun is at a lower position than before, is that the sun has moved closer on the same line that we extended from the shadow. So this is how the sun's position changes as it goes up and down without changing the length of the shadow. So from one instance where the sun is 1 map unit away to another instance where it's lower by a certain percentage, we see that it remains on that line that we extended for the shadow, but all the distances have changed by the same percentage. The angle hasn't changed. This cone remains the same at the same angles. It's only that the cone is now shorter and the sun has moved closer. So again, when the sun moves, it goes up or down, there's a percentage change in its altitude, which is also reflected in the sizes of the circles, its height, and the distance between our location and the location where the sun is directly overhead. So we have to modify this picture now and these measurements by a certain percentage. And what we'll do is we will change the radii of all the circles by a certain percentage, keeping the red circle passing through our location, because it must, until the green circle passes through Santiago. And we find out that if we move the center of these circles by this percentage to that position, and we expand all the other circles by that percentage, Santiago's circle now passes through the known location of Santiago. So everything grew larger, the circles became larger, the sun is further in this example. And now we can add the elevation angle circles for the other cities. So let's do the black city. We'll use the same center. We must adjust its size by the same percentage. And now we have 2 possible locations for this city. One is over here where these circles intersect, and one is over here where the 2 black circles intersect. And we can do the same thing for the blue circles, the other city. We see that the other city's circles intersect here or here. In other words, one city lies here or here, and the other city lies here or here. We already know where Santiago is and where our location is. In order to pinpoint the location of the blue and the black cities, we are going to take a measurement at a third time and repeat everything. Again, we may have to adjust for the height of the sun. So we get new circles, and now you see we have Santiago, we have ourselves, and we see that the blue circles all intersect over here, but not over here. The black circles all intersect over here and not over here. So we can mark the positions of the other cities now. And now we have 4 cities plotted. We can mark them, remove all the circles from our map, and there is now a representation of the real world on our map. The relocation of each of 4 cities plotted. And this represents a scaled version of what's going on in the real world if the Earth is flat. This method uses simple Euclidean geometry to plot a map for a flat Earth, using nothing more than a stick. This is the tool that the Greeks and the Egyptians had 2,500 years ago and more. One exception: they did not have access to instant communication. With the cell phone technology, internet, video conferencing, voice over IP, there is no excuse. We should be able to arrange and coordinate thousands of measurements simultaneously across the span of the Earth and get accurate data to start plotting the coastlines of the continents by merely plotting the positions of cities and villages and towns and landmarks. This method is simple and infallible and incontestable. If the Earth is flat, it will give you a very accurate map of the Earth. You can also repeat this experiment on a smaller scale. You can test it out in your living room, hang a lamp from the ceiling, put a few shoes down as locations, and use a stick and start measuring shadows of the stick from the lamp at the various shoes and try to plot a map of your living room or your backyard or your deck, wherever you have a flat surface. This method is simple triangulation based on Euclidean geometry. In the next video, we'll cover real-world data and completing an experiment to plot a few cities in America. And I'll show how that turns out. Thanks for watching What If the Earth is Flat?